Alright, we've got 4 Python mini projects lined up back to back today. The birthday paradox, a bitmap message tool, Blackjack, and finally, a bouncing DVD logo. We're going roughly simplest to trickiest, so you build confidence early before we get into the more visual, stateful stuff at the end. Put 23 strangers in a room. Odds are 2 share a birthday, not the year, just the month and day. Sounds fake. It's not. We're building a simulator to prove it and figure out why your gut gets this so wrong. It's called a paradox because it isn't one. It's just surprising. Your brain does a rough 36.5 divided by 2 and lands on 83 people needed. That number is wrong, and figuring out why is more interesting than the answer itself. Here's why. 83 feels right. We picture ourselves in the room, waiting for someone to match our specific birthday. With only 23 people, the odds of that happening are tiny. But that's not the question the paradox is asking. Here's the trick. Stop thinking about yourself and start thinking about pairs. It's not one person hunting for a match. It's every possible 2-person combination in the room, all checking simultaneously. With 23 people, you don't get 23 chances at a match. You get 23. Because that's how many unique pairs exist. Pair count explodes way faster than the people count, and that's the entire engine behind the paradox. Directly computing probability some pair matches is messy. There are too many overlapping ways it can happen. So, we flip it, compute the probability that everyone has a different birthday, which is much cleaner, then subtract that from 1. We build this probability person by person. The first person can land on any of 365 days, no constraint. The second person has to avoid the first person's day, so it's 364 out of 365. Each new person has 1 fewer free day than the last. Instead of writing out each multiplication by hand, we loop it. Each iteration knocks 1 more day off the numerator. Then the match probability is just 1 minus that. This is the whole mathematical core of the simulator in 6 lines. Run this for 23 people, and you get about 50.7%, just past a coin flip, exactly matching the famous claim. And it sanity checks at the edges too. 1 person alone has 0 chance of matching anyone. Plot this probability against group size, and you don't get a straight line. You get a curve that stays flat early, crosses 50% almost exactly at 23, then rockets upward. That steep bend is the pair count explosion, made visible. Push the group size a bit further and the odds go from surprising to inevitable. At 70 people, the probability of a shared birthday is 99.9999%. You'd have better luck finding a unicorn than a room of 70 strangers with 0 matches. This isn't just trivia. It's the same reasoning behind birthday attacks on hash functions. A hash space might look astronomically large. But because you're checking pairs of hashes, not single matches against a target, collisions show up far sooner than intuition suggests. It's why cryptographic hashes need way more bits than you'd naively expect. Think of a hash function as a fingerprint machine. Feed it any file, get back a short fingerprint. An attacker doesn't need to match one specific fingerprint. Just find any 2 files that print the same. Exactly the pairs trick from before. That's why real fingerprint spaces have to be way bigger than intuition says is safe. Honestly, the first time I coded this up, I made the same mistake the intuition makes. I checked each person against a running list instead of thinking in pairs from the start. It still worked, but it took me way longer to trust the numbers than it should have. First time I coded this, I only compared each new birthday to the person right before it, not everyone already in the room. It ran fine, gave plausible looking numbers, and was just quietly wrong. Same mistake the intuition makes, thinking one person at a time instead of every pair at once. The birthday paradox isn't a trick of probability, it's a trick of framing. Pairs grow far faster than people, and that's the whole story. The trick was hard to find. The subscribe button isn't hiding. If something feels off or missing, or you want to see something new, tell me in the comments. Alright, first up, let's crack open the Bitmap message project. Take a look at this photo. Looks completely normal, right? It's not. Somewhere in these pixels there's a text message hiding in plain sight, and by the end of this build you'll know exactly how to put one there yourself and pull it back out. The plan is short. Text becomes bits. Bits get tucked into pixels, we save the image, and later we walk the same pixels in the same order to pull the bits and the text back out. 4 steps, nothing more. Strip away the word image, and a bitmap is just a grid of numbers. Every pixel is three values: red, green, blue, each one an 8-bit number between 0 and 255. That's the entire canvas we get to work with. Here's the trick. Every color value is 8 bits, and the very last one, the least significant bit, barely matters to how the color looks. So instead of storing color there, we store one bit of our message, one pixel, one hidden bit. Watch this. The message gets flattened into a long stream of bits, and we warp the pixels one at a time, dropping a single bit into each one's least significant slot. It's a slow, boring conveyor belt, and that's exactly why it works. This is the whole encoder. We turn the message into a bit string with a 0 byte on the end as a stop marker, then warp pixels left to right, top to bottom, overwriting each red channel's last bit with the next bit in line. Once we run out of bits, we just stop. Honestly, this is the part people find hard to believe until they see it. Nudging a color by 1 out of 255 is nothing. Your eyes just can't catch it. My honest take is that steganography like this is underrated as a teaching tool, because the math is simple but the result genuinely looks like magic. Decoding is just encoding in reverse. Warp the same pixels, grab the last bit of each red value, and you rebuild the exact bit stream we wrote. I'll admit I once decoded the green channel instead of red and burned an hour wondering why my message came out as garbage. Order matters, both ends have to agree on it. There's no free lunch here. One pixel holds one bit, so your message length is capped by how many pixels you've got. A small thumbnail might hide a sentence, a big photo could hide a paragraph. Here's the part that should freak you out a little. The next stock photo you download probably already has an invisible tag hidden in its pixels, the exact same way, so the seller can prove it's theirs if you steal it. Journalists have used this same one-bit trick to slip messages past censors who were only checking what a photo looked like, not what it was hiding. You didn't just learn a toy exercise. You built the real thing. Zoom out and the whole thing is 4 honest steps. Text to bits, bits into pixel LSBs, LSBs back out, bits back to text. Nothing about it is complicated. It's just patient and precise. Clean. Put both functions in one file and you've got the whole program. Encode a message into any image, then decode it back out. This is the version I'd actually ship. Run the script and you'll get a new image file that looks pixel for pixel, identical to the original at a glance. Call decode on it and your message prints right back out to the terminal, no worse for wear. If you want to take this further, use all 3 color channels instead of just red. That triples how much you can hide in the same image. Layer in some basic encryption before encoding, and you've got something that's both hidden and locked. This problem had a trick. Subscribing doesn't need one. If something feels off or missing, or you want to see something new, tell me in the comments. Cool. Now, let's shift gears and build ourselves a game of blackjack. One set of decisions can shrink blackjack's house edge 10 times over. Every other casino game is fixed odds no matter what you do. Blackjack is the one where your choices actually move that number. We are building a playable version from scratch so you can see exactly which decisions do the moving. Before any code, let's nail the one goal. So nothing later feels arbitrary, beat the dealer's total without busting. That's it. Every rule we add, card values, hit, stand, the dealer's forced play, exist only to serve that single objective. Number cards are exactly what they say. Face cards are flat, tens easy so far. The ace is the interesting one. It's worth 11 by default, but it reflects down to 1 the instant you need it to. We'll build that flexibility into the code in a minute. Think of it like a restaurant menu that lists every size paired with every flavor. Small vanilla, small chocolate, medium vanilla, and so on. That's all this one line does. It pairs every suit with every rank to generate all 52 combinations at once. No card class required. Shuffle it once and we're holding a ready-to-deal deck. Dealing is simple, but the hidden card matters. Player sees both of their cards, but the dealer only reveals one. That's what makes the player's decisions real choices under uncertainty, instead of a solved math problem. You're deciding without full information, same as the dealer's whole card in real casinos. A real casino table gives you 4 moves each turn. We're building the 2 that carry the actual logic, hit and stand, and leaving double and split as a chain extension point, since they're really just variations on the same hit-stand loop with a different bet attached. Here's the trick. Count every ace as 11 first. Then if you bust, knock it down to 1 ace at a time until you're back in bounds. I used to hard-code aces as 1 early on and kept miscounting soft hands. This two-pass approach handles it in one clean function. Clean. This loop is where the tension actually lives. Every hit is a real gamble, because the moment your total tips past 21 the hand is over, no matter what the dealer is holding. That immediate, no takebacks loss is exactly why Blackjack feels sharper than most card games. I used to assume the dealer had some judgment call at 17, like a real player would. They don't. It's a fixed rule. Under 17 they must hit. At 17 or above they must stand, full stop. That mechanical constraint is exactly what gives the player's free choice its value. You get to think. The dealer doesn't. The dealer's turn reuses hand value with no new logic. It's just a while loop with a fixed threshold instead of a human deciding. Deciding the winner is 4 comparisons. Bust, dealer bust, higher total, or a tie. Nothing here needed to be clever. There's one shortcut to instant victory. An ace plus any 10 value card in your opening. 2 cards is a natural 21. And real tables pay that out at 3 to 2 instead of even money. We are keeping the build simple and skipping that payout wrinkle, but it's a natural next feature if you want to extend this. Put together, this is maybe 60 lines and every one of them earns its place. No splitting, no insurance, no bet tracking, just the core game loop. Nothing here is more than a few lines because we kept each piece doing exactly one job. Right now, every hand you play is disconnected from the last. Win or lose, your money resets. Add a bankroll variable and suddenly a bad decision on hand 3 costs you something real from hand 1, which is the whole point of basic strategy existing. Double down and split are just 2 more branches in player turn. The hard part, hand value and the game loop, is already done. Here's my honest take. Card counting gets all the movie glory, but it's overrated for anyone starting out. Basic strategy. A fixed chart telling you the correct move for every hand versus up-card pair. Closes most of the house edge on its own, and it's just data you memorize, not a skill you train for years. The natural next step is double down and split. Both slot into player turn as new branches. They don't need a rewrite. Add a running bankroll and you've basically got the full casino game. And to wrap things up, let's have some fun with the bouncing DVD logo. Alright, we all stared at this logo waiting for the corner hit that never comes. Today I'm building the actual program behind that meme from scratch. It's a tiny project, but it's a genuinely good one for learning how motion and collisions work in code. Let's whiteboard it. Strip away the nostalgia, and this is a short list. State, movement, collision, and 1 cosmetic bonus. 4 pieces in that order. Everything else is just window dressing on top of those 4 ideas. Peel off the branding. And this meme is just a shape moving at constant velocity inside a bounded box. No AI, no physics engine, nothing clever hiding under the hood. It's one of the simplest simulations you can write. The logo doesn't need a brain, it needs 4 numbers, its X and Y position, and its X and Y velocity. Everything you see on screen falls out of just updating those 4 values every frame. Here's the update loop, and it's almost embarrassingly small. Add velocity to position every frame. Before we've written a single collision check, this already looks like motion. Everything after this is just teaching it where the walls are. Think about a ball bouncing off a wall in real life. It doesn't stop dead, it just reverses. Code does the same trick. Flip the sign of that axis velocity, positive becomes negative, and it walks back the way it came. First time I wrote this, I flipped both Vx and Vi on every hit instead of just the axis that crossed, and the logo snapped into a full reverse instead of sliding along the wall. 1 axis at a time. This is the whole collision system. Check the left and right edges. Flip Vx if either one's crossed, then do the same for top and bottom with V. No corner detection magic, no look ahead. Just 2 independent checks that don't know or care about each other. The color change on every bounce feels like part of the logic, but it isn't, it's cosmetic. You could delete it entirely and the logo would still bounce exactly the same way. It's there so your eye can actually register that a bounce just happened. Here's the twist nobody expects. There is no corner detection code anywhere in this program. None. The X check and the Y check are 2 totally separate if statements that have no idea. The other one exists. For a corner hit, both would have to cross on the exact same frame by accident, and with the logo's real proportions, that's basically a coin flip landing on its edge. The internet has watched this for years, waiting for something that was never designed to happen. The odds aren't fixed, they shift with screen and logo dimensions. A near square window gives the diagonal path more chances to land exactly on a corner, while an ultra-wide screen makes it almost impossible. Same code, very different luck depending on the box you put it in. This is everything combined into one runnable program. The state, the update loop, the two collision checks, the color swap, all wired into a real Tkinter window. Run it and you'll watch the exact logic we just walked through play out on screen. Fire it up and you get exactly what you'd expect. The logo drifts, taps a wall, flips one axis, swaps color and keeps going. Watch it long enough and you'll see plenty of edge bounces and, if you're patient, maybe one corner. Clean. A fun follow-up. Keep a running counter of corner hits and display it on screen. Leave it running for a while and you turn the meme into an actual experiment, watching just how rare that corner really is. So here's the one-line mental model to keep bounded motion plus a sign flip when you hit an edge. That's the entire trick behind a meme people have watched for years. That's the hard part explained. Here's the easy part. Hit follow. If something feels off or missing or you want to see something new, tell me in the comments.